Let's continue our journey from the stomach into the small intestine. And so the small intestine is where the majority of nutrients from food will be absorbed. And the first region of the intestine, the small intestine, that we will see, we've already talked about in detail, is the duodenum. And that's that first 10 inches or so that's mostly retroperitoneal that will be receiving the chyme from the stomach as well as buffers and enzymes from the pancreas and bile from the liver. The next region is called the JEJUNUM, and this is where we're going to see the majority of absorption occurring. And the JEJUNUM is going to have histology that's highly folded. So we're going to see our plicae circularis here, and we're going to see our villi here, and we're going to see a vast increase in the surface area so that we can absorb the nutrients and produce enzymes. And the last section is called the ileum, and the ileum is going to be where this highly increased surface area is going to begin to flatten out a little bit. And we're not going to absorb anywhere near the number of nutrients that we did in the jejunum. We'll still see some absorption of things such as vitamin B12, for example. But what we will see is we'll see some mucosa-associated lymphatic tissue called Peyer's patches. So some of that malt tissue will be found in the ileum. So the duodenum, as we've said, is that first 10 inches or so that's receiving all the chyme from the stomach as well as enzymes from the pancreas and the buffers from the pancreas such as bicarbonate and also our bile. One of its main functions is to neutralize the acids before they move on further through the small intestine. Once we get to the jejunum, that is very sensitive, and that epithelium is not nearly as protected as what's in the duodenum. And remember, the epithelium of the duodenum isn't even as protective as what is in the stomach. So the duodenum is going to be kind of a transition area where we're going to be taking a very high acidity, low pH substance, and we're going to bring it more toward neutral and even into alkalinity. So we've got several hormones that are going to be secreted by the duodenum as well. So remember our enteroendocrine cells that are scattered throughout our epithelium along the gastrointestinal tract. Some of these hormones we've seen before and we've discussed before. So let's just take a look at each one of them. Gastrin is sometimes secreted by the duodenum as well as the stomach. So we still have G cells in the duodenum as well, and they will start to produce gastrin if the chyme coming into the duodenum has incompletely digested proteins or large proteins that haven't really been broken down that well. And the reason is it means that the stomach hasn't really spent enough time on them yet. So we want to encourage the stomach to do more protein digestion before it dumps those contents into the duodenum. So in this respect, it's going to increase the secretion of acids and enzymes that are going to be helpful in breaking down those proteins in the stomach, and also increase the motility in the stomach to increase the mixing and churning and allow those enzymes more surface area to work. And so if that chyme comes into the duodenum and there are a lot of undigested proteins in it, then the duodenum will send a feedback signal to the stomach that says, hey, you need to break these proteins down a little bit better before you send them on to me. The other thing we've seen before, secretin, and this is simply when chyme arrives in the duodenum, it's going to increase the production of bile by the liver and the secretion of bile, and it's also going to increase buffer secretion from the pancreas. We've got gastric inhibitory protein, which, as we know, is going to tone down the activity of the stomach, and this will be secreted when fats and carbohydrates are entering the duodenum. We also have our cholecystokinin, which we talked about last time, and this is produced when the chyme contains lots of lipids and partially digested proteins, and that's going to allow for the secretion of bile. So basically, it's going to stimulate the gallbladder to contract. And it's also going to open up that hepatopancreatic sphincter, which allows for the bile to enter into the duodenum as well as secretions from the pancreas. And this is going to be important because if we've got lots of lipids, then we're going to need to emulsify those lipids and break them down into small droplets so that our lipases can act on them. We also have vasoactive intestinal peptide, and as the name implies, it has some effect on blood vessels. And what it does is it causes a dilation of regional capillaries, and this is going to allow for more absorption. So once we absorb things, then we can move those things into circulation. And so as we'll see a little bit later, and as we've discussed before, the nutrients that are absorbed are first going to go either to hepatic portal circulation into the liver, or if it's lipids, they'll be packaged into chylomicrons and then put into the lacteals, which are lymphatic capillaries. We also have enteroendocrine, and this is going to stimulate the production of mucins by the submucosal gland of the duodenum. And that, of course, is going to create a mucus coat that is going to protect the duodenum from the acidic contents of the stomach. All right, moving on from the duodenum, we can move into the JEJUNUM. This is where most of our absorption of materials is going to happen. And this is where, actually I see a mistake here. JEJUNUM has quite a few plicae circularis, and it has some fairly pronounced villi. Both of these actually are relevant to the duodenum, not the JEJUNUM. So I found a mistake on the slide. So the JEJUNUM is going to be the one that has highly folded plicae circularis and villi. The ileum is going to be the last and longest segment of the small intestine, and it's going to end at this area called the ileocecal valve. If you recall from previous discussions, the ileum is going to empty into the first part of the large intestine called the cecum, and it's going to have a little sphincter there that is going to allow for the contents of the ileum to move into the first part of the large intestine. All right, so here's a picture of it. Here we have our duodenum in blue, we have our JEJUNUM in purple, and here notice they've cut away a section so you can see the plicae circularis inside. And then we have the ileum here. This is the longest section. And notice how it ends here at this first little pouch-like part of the large intestine called the cecum. And as you recall before, the cecum has this vermiform appendix hanging off of it. It looks kind of like a worm. And this too is mucosa-associated lymphatic tissue. So you're going to have your Peyer's patches all throughout the ileum here, and you're going to have the appendix, which is also mucosa-associated lymphatic tissue. All right, so let's look at the small intestine, being reminded that we have our plicae circularis and our intestinal villi, and these are going to increase our absorptive surface area. So if you can imagine, the luminal diameter alone would give you an absorptive area of about 3.6 feet square. Well, it's not that much, but if we add in these plicae circularis and intestinal villi, and we take into account the fact that the apical surface of the simple columnar cells also have microvilli, we can increase that surface area to about 2,200 square feet, which is quite a multiplication. So here is a histological showing, well, I guess, showing the organization of it. And here you can see the plicae circularis, and if you zoom even more, you can almost see the little villi in here. And here they've taken out the plicae circularis. You can see the villi. There's a plicae circularis out of this one segment here. And if we zoomed in even closer still, now we can see the villi. Now you can see your epithelium here. And remember, the epithelium itself is coated with microvilli. And you can see your lamina propria here, our muscularis mucosa, our submucosa, and so forth. We have got our circular layer of smooth muscle, and we have our longitudinal layer of smooth muscle as well. All right, so now let's look at one of these villi. Now you can see the individual cells are going to have microvilli, and we have our capillary network, our blood capillary network, that's going to be important for absorbing nutrients such as carbohydrates and proteins, or amino acids at this point, and it's going to put those simple sugars and amino acid monomers and nucleic acids and so forth, it's going to send those to the liver via hepatic portal circulation. And of course, we have our lacteal here. This is what's going to receive our chylomicrons, which are our lipids, which are too big, really, to go into circulation here at the capillary. So they will be packaged up into chylomicrons and sent first through lymphatic circulation, and then they will be entered into venous circulation via the thoracic duct of the left subclavian artery. As a quick reminder, here we have a nerve shown up here, and this is going to regulate such things as movement of this villus so that it can sort of mix the contents around locally, and that's going to allow enzymes that we have all along the surface of these things called brush border enzymes. You remember our brush border comes from the fact that the microvilli make this very, very sort of, well, brush border, for lack of a better word for it. Anyway, so we're going to have some brush border enzymes, and these are going to take very small molecules that have been broken down to very small components like disaccharides and break them down into monosaccharides, small peptides and break them down into amino acids and so forth. So our brush borders are going to be very important. And of course, all through here, we're going to have mucus secreting cells because we're going to need to keep this place lubricated, and we're going to need to keep things moving through. All right, so we've got intestinal glands that are going to be secreting the mucus, remember our goblet cells, and we're also going to have some brush border enzymes that we talked about before. We're going to have some really deep intestinal glands too. We've got our goblet cells that are sort of scattered throughout the epithelium, but we're going to have some intestinal glands where we're going to produce mucins. We're also going to have some stem cells in these intestinal glands. These intestinal glands also go by the name the crypts of Lieberkühn. So if you hear the term crypts of Lieberkühn, it's going to be referring to these intestinal glands. And we're also going to have an area where a lot of times when the stem cells are produced in deep within the crypts, they'll be moved up into the epithelium in the villi, and then what's going to happen is some of the cells, they'll replace cells at the tip of the villi that will be shed into the intestinal lumen, and they will then be dissolved there, and all their brush border enzymes and enzymes within those cells will be released and can also get to work on the material that's in the small intestine. All right, so as we've said, we've got our brush border enzymes, and these are surface membrane proteins that are going to be breaking down small molecules. We have something called enteropeptidase, and this is important because it will activate a pancreatic enzyme. The enzyme itself is called trypsin, and it's going to activate the proenzyme trypsinogen and turn it into trypsin. We also are going to have some enteroendocrine cells that are going to be producing hormones like gastrin and cholecystokinin, as well as secretin. All right, so our duodenal glands, if we go back a little bit, I've already talked about the crypts of Lieberkühn, which we find in the JEJUNUM quite a bit. We have duodenal glands that are also called Brunner's glands, and these are submucosal glands, and these are going to be producing lots and lots of mucus. And this is important because when the chyme comes from the stomach, it's going to be quite acidic. Once we get the chyme from the stomach, and of course remember that the stomach basically mixed up gastric juices with the bolus that came from the mouth and down the esophagus, now we have intestinal secretions called intestinal juice. And this is about 1.8 liters a day. And this is going, again, to moisten up the chyme. It's going to assist in buffering the acids, and it's going to keep the digested enzymes and products of digestion in solution. Remember, enzymes have to be in solution to work, and we're going to have some kind of aqueous solution for all this stuff to happen in. All right, so obviously we're going to have a lot of intestinal movements. A lot of these are set in motion entirely by the enteric nervous system. And we have some pace setter cells that just are spontaneously going to depolarize and start movements along this muscular sheet. And that's going to move, we're going to have some peristaltic contractions that are going to move the bolus and the chyme from the duodenum towards the jejunum, and then later from the jejunum towards the ileum. So it takes a while for stuff to happen. So by the time stuff comes into the duodenum, then it's going to take about 5 hours. So these contractions aren't that rapid. It's going to take about 5 hours to pass from the duodenum to the end of the ileum, and this gives those digestive enzymes plenty of time to work and plenty of time for those nutrients to be absorbed. So we're going to have a lot of stirring and mixing of intestinal contents, and sometimes remember that mucosa muscularis mucosa, that will cause really local movements of the plica circularis and the villi, which will allow for stirring and mixing of intestinal contents locally.